Good morning. My name is Philip Martin. We're going to be talking about the name of the talk, which I'm going to apologize for in a second, is Docker Incident Response and Containerized Immutable Continued Deployed Environment. I thought this was funny, but I've been informed by a number of people this is the worst dad joke they have ever heard in their entire lives, and I should feel bad for having put it on the screen. So I'm sorry. I'm not actually sorry, but cool. So. Quick bit about me. I'm a security guy at Coinbase. Coinbase is a digital currency company. We store about $5 billion worth of Bitcoin, Litecoin, Ethereum. So these are digital assets moved online. Just quick show of hands. Digital currency, familiar with it? Okay, like 10%, maybe 20%. Cool. The important thing to remember, I'll talk about this a little bit later, is that both the good thing and the bad thing about digital currency is if you lose it, it's gone. There's no getting it back. There's no second chance. There's no call up the other guy and say, hey, just kidding about that wire transfer. Like, send that back. It doesn't happen. I've been messing around with this sort of like, I don't like the term DevSecOps because I don't like DevOps to begin with, but I've been messing around in this space for quite a while. Occasionally I write some open source software. It's on GitHub. So let's talk about first what we're not covering, because this like could literally probably be a several day presentation if we covered every aspect of all the things, AWS security, secure Docker configuration, SDLC impact of containers, blah, 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 blah. So we're not going to cover any of this stuff. We're going to focus specifically on the incident response impact of existing in this kind of environment. Right? We're going to talk about, first of all, a little bit of context on the environment that we've built. Because sort of that context drives the solutions we've come up with and is overall useful. We're going to talk about things that existing in this sort of containerized, immutable, continuously deployed environment, like either make easier or make much, much harder in the context of preparation, of detection, and of response. So first, one more quick little poll. Who's messed with containers in prod before? Like 5 hands. Cool. How about immutable deployments? Yeah, 5 hands. And how many of you have had the pleasure or pain of working in a continuously deployed environment from a security perspective? Maybe 1 or 2 hands. Cool. So let's talk a bit about those concepts for 1 second before we dive into sort of the rest of the meat of this talk. First, we'll talk about containers, right? I'm using the terms Dockers and containers here interchangeably. They're not. Docker is a implementation of a container. If you're an old school Unix guy, BSD jails, Solaris zones, very, very similar concept. All this is a way to segment a few processes in a larger environment into their own little piece of a running OS. The important difference between containerization and virtualization is in a containerized environment, you share the kernel with the host OS, right? So kernel clones still work, but the user land can be entirely different. So for example, you may be running an Ubuntu host and an Alpine Linux base or a CentOS container base or a Gen 2 container base. It doesn't actually matter from the user land perspective. Immutable deployments. This one's a fun one. So the concept here is when you deploy a thing, it should never change again after that deployment, right? So an example here would be if you deploy a service to prod, that service has a bug in it. A lot of times, what you're going to do is go hop in, maybe monkey patch something in the running instance, or potentially you just deploy some more code to that same instance, right? In an immutable environment, neither of those things happen. What you do is hopefully you find the bug in dev, not in prod, and then you redeploy the entire stack from the ground up. So we'll talk about how we do this at Coinbase specifically, but like new vert, new containers, new security groups in AWS, new ASG, whole 9 yards from the ground up. This has some really cool sort of security impacts from making an attacker's life really annoying, and some really painful security impacts around patching and software updates and things like that we'll talk about. The last, continuously deployed. The concept here, this was the thing that I think I saw the fewest hands for. The concept here is the gap between merging code to master and that code being in production is as small as is technically possible. In most cases, the gap is the length of the test suite, basically. So as an example of this, when we deploy services in Coinbase, we'll talk about this way more in depth, but the gap between merge to master and running in prod is about 30 minutes, which is what it takes for the test suites and securities checks and all that stuff to run. And we do that something like 12 times a day. If you combine that with the immutable deployment concept, what this means is we are rebuilding from scratch internal services 12 to 20 times a day. Again, pluses and minuses there we'll dive into in depth. So real quick, there wasn't a lot of folks who have dealt with this live and in person yet. So let's talk about like why we should care. I cherry-picked two terms, Docker, CI/CD, its acronym, continuous integration, continuous deployment. If I'd picked, I did this for a bunch of other things that just didn't all fit on the slide. They all look like these graphs, right? Up and to the right. Interest is only increasing. These are Google search trends, by the way. Interest is only increasing. These are only becoming more popular. Developers are only moving more quickly toward these things because things like Docker, they enable much cheaper cost. So if you're sharing a host OS with lightweight containers, you can stack more of it on a host than you can the virtualized same service. CI/CD makes iteration times much faster. These are things developers want, and these are things that we're going to have to deal with as they show up in our workplaces. Cool. So let me first, before we dive into like the various problems, opportunities, and things that we've built here, let me give you some context overall about Coinbase and the environment in which we operate. I'm actually not going to reference this network map at all. It's just pretty. So first of all, and if you're interested in this stuff, our infrastructure team does a ton of blogging and talking about this. You can Google a bunch of this stuff and find more details than you'd ever want to know about sort of how we run our infrastructure. But first of all, we're entirely in AWS. 100% of our hosts in production, dev, test, all that stuff, that's all in AWS. So everything in our environment's either on an EC2 container or as a service provided by Amazon. Every piece of code in our environment is deployed in a Docker container and built sort of via our build pipeline. We follow an immutable deployment concept. Every time we deploy, each one of those pretty little squares on the diagram there, that is a full rebuild and tear down with nothing in common between deployments. Right? So an example there, we deploy the service that hosts Coinbase.com. It's one of those boxes somewhere. What actually literally happens is we spin up 20 new instances in EC2. We pull new containers into those from the new code base. We do what's called a blue-green deployment, which is we roll traffic using the load balancer from the old stuff to the new stuff, and we tear down the old stuff, never to be seen again. We do this, like I said before, it depends on the service we're running and like how popular, how much dev time it's gotten, but between, I'd say, 15 and 22 times a day for the more popular services. For the less popular, we do it maybe once every couple of days. Now, like I said before, we're not going to talk about a bunch of stuff. One of the things we're not going to talk about is the whole software security stack that follows along with this, the stack analysis, the dynamic analysis, all that fun stuff. It's actually really, really interesting, and it's a whole separate talk. Maybe I'll give it next year, but it's a little bit outside the scope of the sort of the IR focus here. The next thing we do is we segment most of the Docker details from the engineers. The engineers just want to write code. They don't want to deal with like 50,000 other things about Docker and security groups and firewalls and all that shit. So we segment all that out from them. They have to do like 2 or 3 basic things in a Docker file in their project. That's it. And that also means they don't have control of anything below that stack. We'll talk more about this later too. Let's see. Yeah, so we've done a bunch of work around this stuff to make our environment friendly to this stuff. A lot of environments, and we'll talk about this, are not like Coinbase. When containers and these concepts first roll into organizations, frequently it's the wild, wild west. Right? For example, If you're an organization where a dev team decides, hey, look, I want to use containers, you have this beautiful managed host OS, right? It's patched, it's updated, it's security scanned, it's gorgeous, best thing in the world. And then suddenly you have rando like Gen2 containers and some CentOS containers and maybe an Alpine container and stuff you didn't even know was there, right? And none of the scanning tools you use are going to pick up what's inside a Docker container, and then it's just pain. Because as soon as one of those is popped, you hop on the box thinking, yep, I got my plan, I got my IR, we're ready to go. And you're like, what's this Gen2 thing? Where did this come from? I'm not set up to use Gen2, it isn't logging right, it's doing none of the good things. So we're going to talk about how to solve that problem. I see a couple of people laughing in the audience while I said that. I think you're sharing my pain. Cool. We are more or less on time. Awesome. Let's see. So the first step to great incident response is preparation, right? Like anything else, you want to make sure that before you ever roll into an incident, you have the right knowledge, the right tools, the right processes. It's practice, like you're good to go. So let's talk about preparation in the context of containers. Like if you look at any set of security standards anywhere, right? The CSC20, the Australian government one that's pretty cool, any of them. Somewhere on that list, probably near the top, is going to be, hey, you should know what systems and software you're running. Because that's going to inform like how you do incident response, the tools you use, all that fun stuff. In the situation I just talked about, right, where a couple of dev teams somewhere suddenly installed like rando software that's not scanned, it's not patched, not updated. How do we take that situation and then walk that back to a place where you're walking into a situation that you understand and where you have the tools and processes ready here? So first of all, and most important for us, has been to establish managed base containers. So the containers, especially Docker, have this concept of layering, right? So container A is layered on B, is layered on C, is layered on D. What this means is you can call it like a base CentOS 7 container, right? Where you install Node support, Go support, Ruby support. That's 3 separate base containers, very thinly layered on top of this one base container. And you can continue layering on top of previously existing containers essentially infinitely, right? This is pretty cool because this means I can control the base OS container and I can let my developers just sort of layer on after that. I get to control sort of the core OS of what's going on, and I get to control it at a very fine-grained layer. The second piece there is sort of related. We don't allow people to deploy rando containers in our environment, and I would encourage you not to as well. The Docker Hub, if you go look at it, is really cool. There's a lot of prepackaged software there. In fact, and this was actually the genesis of this talk, if you go Google Docker incident response, what you're going to find are about 5 pages of Google about containers that you can use during an incident response, as opposed to any information about incident response involving Docker. All those containers are super awesome, really cool. You have no idea who built them. You have no idea who set them up. You have no idea what base containers they were built upon or what software is installed in them. I would encourage you not to let them run in your environment because of that. So these 2 things actually have alpha support in several of the orchestration layers, right? So these are things that say, hey, this container runs in that place and it runs this software version. One of the most popular ones is called Kubernetes. It's from Google. It's what they say. It's what GCP, their Google Cloud Platform, is based on. It's based on I think, much more developed version than is of the Kubernetes that is open source. So there's alpha support there. We've actually had to build our own thing, which is on the way to being open sourced. There are obstacles. But those 2 controls, if you end up in this environment, I would encourage you, are the most important to making sure the environment you run in is the environment you think you're running in. After that, so Claire is a really fun project I should talk about briefly. Claire is a vulnerability scanner for containers. It is specifically built to work with Docker, and you can point it at a Docker container, and it will go down layer by layer and tell you, hey, this container is running this software, which has this CVE associated with it, you should fix that. It'll also tell you whether that layer is actually exposed, right? So this layering concept has one interesting side effect. That is, what if you have a base layer that has a version of OpenSSL installed, right? And you get another layer on top of that that has a different version of OpenSSL installed. Well, the end container has that second version of OpenSSL exposed, but that first one is still there. And if some point in the future the developer decides, I actually don't need OpenSSL anymore, then suddenly magically the version below that is exposed to the world, right? Really annoying. So Claire does a really great job of flagging those sort of proto vulnerabilities as well, so that you can patch all the way up your container stack, right? The next one is also really important. Don't let developers do whatever they want in a Docker file. There's a lot of stuff they can do. For instance, we talked about that vulnerable library, right? So you're running Claire, you're scanning your Docker file, you're making sure all your packages are good to go, everything's beautiful, and then in a Docker file somewhere, an engineer just curls down some random version of a library from the internet and says, hey, I'm going to use this now, right? Not what I want to see in my environment, because when I roll in an incident response, my expectation is that you're running this version of the package, it has these known vulnerabilities or doesn't, come to find that I'm totally wrong because we've curled down half a dozen libraries and everything is all weird. There are a couple of really great, I've referenced one there, there are like 2 or 3 other Docker file linters that are really outstanding at letting you pick apart this stuff and say, hey, don't run curl to bash in a Docker file. Just don't. Just stop that. So all this, the point of all this is, in a perfect world, you will be able to go from the name and version of a package to a list of running containers that have that package installed in a single step, right? And I think that it really gets you on part of a solid foundation to making sure that when you roll in an incident response, you roll into an environment that you expect to be in, not an environment that's completely foreign to you. Another preparation, and this is actually a good thing, not a bad thing. Containers should be single purpose, right? Running in a container generally means you have 1, maybe 2 processes running within a container. It's generally doing one specific job within that container, which means you can dramatically restrict the privileges and the access that container has. And there's a ton of cool tools to do this. So first of all, you can make that managed based OS we talk about can be extremely small. Alpine Linux, I think the default base there is about 10 megs of user land. It actually uses libmusl, not glibc, so you just drop that whole class of vulnerabilities, which is super cool. In some cases, you can deploy a service, if it's a compiled service, using what's called a scratch container, which is no user land at all. So like Go is great for this. Some of our more critical services that we write in Go, we deploy in scratch containers. We deploy the service itself and whatever libraries it linked against, which is really cool, both from a response perspective and from a sort of attack mitigation perspective. Being an attacker in an environment with 0 user land that's continuously deployed, so it rolls once an hour or so, I imagine it could be quite frustrating. Hopefully. That's the goal at least, right? So 2 other things. Capabilities and seccomp are really, really awesome. Capabilities, these are both sort of Linux kernel features that allow you to restrict what a given binary or set of binaries can do. So capabilities let you either drop or add the ability for a binary to do specific things without giving it overall elevated privileges. So the quintessential example here is so say you have a service that's running, it's running on a port below 1024, so you have to be root to bind to that port, except now you don't, because you can just grant that service a capability called netbind service, and it can suddenly bind to low-numbered ports without any of the other stuff that running as root requires or opens you up to, which is super cool. You can do the reverse too. You can take a running process and drop all capabilities except the few you need for that process to actually succeed. Really, really cool thing, underutilized in my opinion. Setcomp is the same thing, but for syscalls. So setcomp allows you to specify a policy that specifically prevents you from calling specific syscalls in specific ways with specific arguments. It's a really complicated syntax, very complicated policy, but it's really, really powerful. So an example here, so the Docker ships with sane defaults for both of them. Its setcomp policy is maybe a little bit more open than I'd like it to be, but compatibility reasons. So Docker ships with a setcomp policy that blocks about 44 syscalls. One of them being ptrace. So if you guys remember the dirty cow Linux exploit that came out about a year ago, I guess, about half the implementations of that depended on ptrace to function. The rest used devmem or something like that. All of those pcap versions, if run within a Docker container, fail because Docker by default drops ptrace in its setcomp policy, along with about 43 other syscalls. Right? Once you really get involved in this thing, you can do what we're starting to do now, which is per service profiling of syscall use, and extending that setcomp drop list a little bit farther. Drop 44 by default. They're about 300 Linux syscalls, more or less. So if you start to actually build these profiles effectively, you can drop privileges much more extensively, and you can do it semi-automatically without having to necessarily deeply involve your engineering staff, right? So you sort of this layer of security they don't have to worry about that is incredibly effective. So if you've not messed with the capabilities in setcomp before, I highly, highly encourage you, go read up. This is stuff built into the kernel. You almost certainly have it. It's built into Docker, very clean ways of interfacing with it. Two of the best mitigative controls you have with containers. And lastly, because we're an immutable deployment concept, one of the really cool things we can do is actually deploy containers fully read-only. So even if we have a use land there that we're interested in, things like that, because our deployment concept says, hey, we're never going to change this after it's deployed, we can just deploy it read-only, prevents a lot of bad things from happening, both malicious and unintentional, and that also means that we can, again, have confidence the environment we're rolling into in a response is the environment we expect to see, or the deviations are bad. So that was preparation. Let's talk a little bit about detection. This sort of, you know what? I'm actually gonna flip the order of these two, because this one flows better from the last slide. Who knows what that thing down there at the bottom is? If someone says audit D, I'll buy you a beer later, because I'm sorry. So because we just talked about containers are single purpose, containers do one thing, right? The first thing I think about when I hear that is, oh my God, does this mean I could do whitelisting? Like really? I think we in security have looked at whitelisting for a very long time as sort of the gold standard. It's really hard to do on an operating system level, as a number of organizations have discovered over the years. It's sort of the white whale of InfoSec. Moby Dick fans, maybe? No? Fair enough. So does this mean we can really do whitelisting inside of a container? The answer is mostly. Certainly more effectively than in a general purpose operating system. So what we do, or what we've been able to build is whitelisting specific syscalls, right? So today in our environment, we whitelist execs, so we whitelist connects. No exec or connect can happen in the Coinbase environment without us having profiled the app in question and previously whitelisted those specific calls. How do we do this? We do this with much pain and crying and drinking using audit D. Audit D is the best worst thing I think to happen to Linux auditing ever. It's the best thing because it's an incredible source of data that you cannot get anywhere else from the system as reliably as you get from audit D. It's the worst thing because that's the actual log format. It's a multi-line format, as you can see there. that uses that number in parentheses is the common key that you can use to associate these things together. And it's just this is actually a fairly simple line. It's just really painful to work with. Let's see. So there are a couple problems with this. Specifically, one is that audit D is not container, or specifically is not C group aware. C groups and namespaces are the fundamental things that allow containers to work in Linux. So audit D isn't C group aware. So you don't see anywhere in that big list of gobbledygook anything about a container name or a C group path or any of that stuff. So how do you map that back? There's two ways. One way is you can play games with the SELinux tag, right? So you see the SELinux context in that log line right there. If you're tagging your containers effectively, even if you're not confining them, if you're just tagging them, that will show up in SELinux, and you can use that to walk back a log line to a container. The other way is via the PID in the log line. You see it there on the second line to the right. At the end of the day, containerized things are just processes running on your box, right? If you do a PS, you'll see the process there on your box. They just have special constraints associated with them. You can, if you maintain a mapping, and you know, this is probably the best way to do it if you don't want to dive into SELinux. You can track a host level PID back to a container name fairly trivially. We'll talk a little bit later in this presentation. I have a set of bash functions I use to make a lot of this stuff easier. The information is all there, but sometimes it's a complicated path to get to it. Let's go back one real quick. So again, single purpose environment, right? And this is the problem with that. There's no real space here for traditional security solutions. You're not gonna install tripwire in a container, right? It's just not gonna work well. So how do you get your telemetry out, right? I mentioned before, we use Audit D. There are probably a dozen different vendors that will tell you they have a solution to this problem. I have varying opinions of them. We're not going to talk about any of them today. A few things that are coming. I'm actually super excited about eBPF. If you guys have not started to research that yet, I highly encourage you to do so. It's an awesome project. It will hopefully be the replacement for Audit D for kernel level logging in Linux in the future. Really cool project. The other things we do is we use a concept called sidecar containers. The words are fairly self-explanatory, but basically when we deploy a host with containers that perform a service, we also will deploy one or two other containers transparently to the users along with them, so that those containers can do specific security things like logging DNS, like doing on-host rolling PCAP that we can use during an incident response, things of that nature, right? This is transparent to the engineers. They don't see it, they don't care about it, they don't deal with it, but it magically sort of helps protect them, and it helps get us in a place where, again, during a response, we have some of the stuff that we might rely on traditionally, like, potentially we have recent PCAP, we have good DNS logs, we have all that fun stuff that we want to have. Let's see. Cool. Let's talk a little bit about detection. I intentionally am skipping like the whole detection pipeline about shoving these things in a pipeline so the logs go to some service that does magic and then alerts that come out of the other end. Because it's not just really relevant to the focus of this talk. But happy to chat about it afterwards if people are curious. So this is an interesting one, and this is, in my opinion, one of the core problems with continuous deployment. If we believe all the reports and what everyone says is attacker dwell time, easily weeks, probably months. If you're in an environment where your host lifetime is hours or days, how do you do a real incident response if you detect it a month later, right? It's actually quite challenging, I think. So we have a few things that we do to make this a little bit easier. One, we log everything. Our log pipeline is probably one of the most expensive pieces of our infrastructure because we log everything. We log every single application log line that happens. We log audit D, every single exec, every single connect, a bunch of other specific targeted things as well. We pull down all the system logs from every single host across the entire environment. And really the reason we do this is because if you think about it, in an environment where hosts rotate that rapidly, you can't really do a hunt on a host anymore, right? Because they're so ephemeral, they're there, they're gone. When we hunt specifically on logs, right? So that our logs have to be very high fidelity, and they have to be good enough so that we can both form a picture and walk back a potential incident, even if it occurred 3 months after we terminated that instance, right? We also enrich, and I think this is quite critical. Even if you're not in this environment, I think log time enrichment is incredibly critical. This environment just makes it more of a problem or more critical, right? Enrich log lines when you log them. That means if I log a line, IP address A, talk to IP address B for this long, this many packets, this many bytes, blah, 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 blah. I should also add on what those IP addresses are at that point, because 3 months later, I guarantee you they either won't exist or there'll be something else entirely, and they'll just screw me up if I try to walk it back, right? And if you try to maintain separate repositories of like IP information going back 3 months and logs going back 3 months, and you try to like fit them together at some point, you're just going to have a huge headache. As opposed to doing a few simple API calls when you log to resolve that stuff. I resolve IPs, resolve PIDs, resolve UIDs, resolve everything that you can reasonably resolve in a log line so you don't have to try to do it later. We keep logs for years. Our standard actually is a 10-year retention. Like, companies hasn't even been around for 10 years. A lot of the stuff falls into Glacier, right, after its liveliness period. But we have it. So if we discover, God forbid, a breach a year later, we can go into Glacier and do a restore and pull back, that month's worth of logs, and when we have the data there to actually do the investigation. Our logging standards are rapidly evolving. So this is actually one thing we don't do that I encourage you guys to do when you're going in this direction, is establish a consistent log schema. Even if your format changes, the data you collect changes, make it all look the same, JSON or whatever, so you have an easier time parsing it, right? One of the worst incident responses I ever had to deal with, not at Coinbase, was where the company in question had changed their logging format in the middle of the incident. So I'm trying to like correlate these logs back. It was a nightmare of manual magic to get even a broad picture put together. So pick a standard, stay to the standard. Otherwise you will have pain later. The last thing we do is a little bit more controversial, both because it has data costs and there are data exposure risks. But for really critical services in our environment, we can treat service spin down events, like when we do deploy, we can treat it just like an incident response event in terms of like the automated things we do, right? We can pull a memory dump. We can pull system artifacts. We can pull all the same things we might pull if there was an incident response, encrypt it, toss it in a bucket somewhere, put it in Glacier, so that again, if we have to go back and deal with it, we have at least some data there. We have a reasonable way of walking that back. Now again, that's a lot of data, right? If you're pulling a memory dump from every single host, if you're pulling the full set of live response system artifacts off a host every time it's deployed once an hour, that's a ton of data. So I would only encourage you to do this in systems that are incredibly critical, that are sort of like the no-fail style of systems. Otherwise, it's going to cost more than it's worth to do. Let's see. Okay, so let's move on a little bit from that to you've had an incident. You're sitting on a box. And you're staring at this Docker container. You've done all this other stuff. What do you do? You've done all this nice prep work. How do you deal with it? So basic question, right? There's an active breach. You're staring at the container. There's an attacker there. How do you isolate it? There are a bunch of ways. I'm going to skip the AWS bit because they're like, you can Google this and find a half a dozen great talks on AWS incident response. So at the host level, there are a few options you can deal with. Docker does have a pause command. You can pause the container. This uses a thing called the cgroup freezer. So it's not what you're thinking about if you're thinking about like a VMware snapshot or checkpoint. It doesn't like take an image of memory. It's literally pausing the processes, right? So you don't get a clean like file you can take away and analyze somewhere else. But the nice thing about the cgroup freezer is the process pause is not visible to the processes being paused, which is pretty cool. It's not none of the standard sort of signal stuff that you would expect. If you're interested, read up. If you just Google cgroup freezer, I think the first result is the kernel docs, because that's, I imagine, an uncommon set of words. Let's see. So that's an option. That's more of an option if if you need to say like, hey, this is an active thing going on right now, but I want to make sure this doesn't get out of hand while I deal with other stuff. Just pause the container and move on with the investigation. You can come back to it later and it won't have changed. Network isolation, right? So running Docker, you don't want to pause it for whatever reason. You want to isolate it from the network so that you can deal with it later. There are several things you can do here. The two basic things, you can isolate it using Docker, you can isolate it using IP tables. Until very recently, Docker 17 and later, Docker and IP tables weren't really friends. Or at least they weren't friends if you also tried to modify IP tables. There was a lot of like, stomp on your changes, there'd be a lot of pain. After 17, you can just drop a rule in this Docker user chain, you're good to go. You can also isolate it using Docker, right? So Docker has this concept of networks. And under the hood, what you'll find is for every network, there's a bridge interface that it creates on the Linux box. When you add a container to a network, it just drops it on that bridge interface with all the other things. And then it can do, depending on how you configure the network, it can talk to the internet, it can't, it's NATed, it isn't. It just connects that bridge to gateway devices. Pretty simple, right? So you can tell Docker, hey, just disconnect this container from all the networks. It'll drop all of the interfaces internally, and it's totally isolated. Except if you're using that little fun thing, network equals host. So network equals host attaches the containers directly to the interfaces on the host itself. You can't change that once you've done it. That is only the smallest reason network equals host can be painful and bad. So I encourage you guys not to use it, and encourage any sort of product teams you deal with also not to use it. It's easy, which is why people do it, but it's a bad idea sort of later in life. The last thing is Docker checkpoint. So Docker checkpoint is really interesting. It's an experimental feature. It's not shipped yet. You can enable it in Docker, and that's exactly what you'd expect. That's essentially just a full snapshot of the host in question. This is what would actually allow a Docker container to be live migrated between hosts, because it is a full portable snapshot of a Docker container. That said, nothing supports it. It's not like you can feed this Docker checkpoint into volatility yet. If there are any volatility gurus listening, please build that. It'd be awesome. But if you do use it, it can be a very, very effective way of isolating this thing for further investigation. And you can take the checkpointed container from a server somewhere where it got popped, bring it back to your system, restart it there. It's nice. It's a very clean way of dealing with it once it hits production. Ooh, getting close on time. Live response. So there are a bunch of standard Docker commands. I'm going to go through this a little bit faster so I make sure I have some time for questions. Standard Docker commands, like there's some really cool stuff inside that it provides. We'll talk about that next slide. But basically, when you get right down to it, that Docker container is just a process on your box. All the same tools that you would use to investigate any other process, in general, mostly work. Because of the way Docker exists, some things like the PID the process thinks it is not the PID it is on the host. File paths that the process thinks it's opening are not the file paths that you would see on the host. Things like that are confused and broken. You can pull most of that information from Docker itself. But the great thing is anything else, like you can attach strace to a process that is a container, and it works like you'd expect it to work, more or less. You can use gcore to force a memory dump, or whatever other your normal process-specific memory dump is on a container, and it'll work. You can even TCP dump a specific container using, we talked about before, right, that whole bridge gateway scenario. It's fairly easy to attach to the right bridge and filter on the right IP address to actually do a specific PCAP on a container, right? Let's talk about these Docker commands for just 1 second. There are a bunch of them, and I'm going to highlight just like 2, and you can read the rest later. One is Docker diff, which will show you the file diff for running container. Like, how great is that? What if there was like a host OS diff that you just run when you're doing a response? Let's see, Docker exec will let you run from the host, run a command inside the container. This is how you can spin up a bash shell inside the container during response and do actual live response there on the container itself. We mentioned Docker checkpoint. That link on the bottom there just goes to a gist of some bash functions I use during incident responses that involve Docker that just automate a lot of some of the more complicated things to pull. Like, for instance, one of the functions in there lets you pull a map of host PID to in container PID for a given container. That just makes forensics after the fact much easier if you know that mapping, right? Things like that. Just in general helps make your life a little bit better. Last one, and then questions. And this is I should have put this earlier so I had more time to talk about it. So in this immutable deployment concept, right, there's this box running somewhere, and I don't have access to it. I have no SSH access. I can't get on it, and it gets popped because reasons, right? What then, ... There are a lot of answers to this question. You could have an immutable deployment concept where there's a break glass involved. That has sort of pluses and minuses there, right? But for us, we don't want to do that. We wanted to actually make immutable. So what can we do? This is what we can do. We essentially have automated incident response scripts that are sitting there. They're monitoring an SQSQ. They're looking for a signed command. We just borrowed what GER does, right? You sign your commands directly with a GPG key, so the host knows it's you. Waiting to kick off an automated IR run on the host itself to say, like, hey, yep, signed requests. Let's do the memory dump. Let's do the running indicators. Do all this stuff. Let's encrypt it back to the key that sent us the command, and let's toss it in S3 somewhere so you can pull it down and do your forensics later without ever having access to the host itself. The reason we do this this kind of thing on very sensitive hosts where access to the host could expose things like private keys that we don't want any one human being to ever be able to see, right? Let's see. With that, I think we have about 3 or 4 minutes, yeah, for questions. Questions? Are you awake? Okay, the laughter says yes. Good. Well, awesome. Thank you all very much, and I guess I will leave you for the break a little bit early.